All right, let's take a look at section 8.3. So this is our laws of logarithms. So before we do any more with this, I think we need to actually go back to grade 9 and grade 10 and look at some of your basic exponent laws and see how that actually connects. So here we just have simplify the expressions using exponent laws. So we have a base 5 to the power of 3 times 5 squared divided by 5. So when you have the same base, then you're going to add the exponents. So we get 5, so 3 plus 2 is 5. And then now that we have the same base of 5, we could put a 1 here. So when you're dividing the same base, then you subtract the exponent. So 5 minus 1 is 4, so you get 5 to the power of 4. All right, the next one. So we're going to do inside the brackets first. Here we have the same base of 3 and a division, so we're going to subtract the exponent. So 6 minus 4 is 2. And we still have that exponent on the outside. So we have power over power. So we actually multiply 2 times 4. So we get 3 to the power of 8. Now the next one's a little bit different. The bases actually aren't the same. So we're going to distribute that 4. There is a exponent 1 on both these. So if it was like 2 or 3, you just do a multiplication. So in this case, it's 1 times 4. So we get 5 to the power of 4. And then 1 times 4 again. So we get 6 to the power of 4. Now these are different bases, 5 and 6, so we can't do anything there. So that 5 is going to stay the same. But here we have same base of 6 and multiplication. So we add 4 plus 2. And so we get 6 to the power of 6. All right, our next one. So we have a division and we in brackets and then a exponent on the outside. So we're actually going to just distribute that exponent to both of these. Again, it's going to be a multiplication just like it was for C. So it's going to become 3 to the power of 5 and 4 to the power of 5. For E, this looks very much the same as your other ones. Here we have a division, same base. Again, we have a 1 here. So 3 minus 1 is 2. What's a little different about this one, though, is now when we go 2 minus 4, I actually get negative 2. And we would normally ask you to reciprocate that, so become 1 over 9 squared. We don't usually want negative exponents at the end. And our very last one, so we get 3 to the power of 5 divided by 3 to the power of 5. So we go 5 minus 5, we get 3 to the power of 0. And then 0 times 4, which is still 0. And we could use an exponent law here as well. 3 to the power of 0 is 1. And so below are some of the generalizations of these exponent laws that were used that you can take a look at. So you might be asking yourself, why are we going all the way back to grade 9 and 10 and you're all the way in 30? Well, it's because there's some of the similar patterns when we're looking at the exponent laws and log laws, and these are related. So then if I look at this first logarithm, log base b and then brackets m times n, it's actually equal to log base b m plus log base b n. Well, that looks awfully similar to this exponent law right here, where we have the same base and we're multiplying, we add the exponents. Well, here, if we have a logarithm and it's being multiplied, well, or something multiplied inside of it, then we can add those two things in their different logs. Similarly, here, if we have a division inside of our logarithm, we would subtract. Well, that looks awfully similar to what happens in our exponent laws when we're subtracting the same base. And we end up subtracting the exponents then, dividing the same base. And then finally we have one where if we have something to the power of something in a log, then that n actually is going to come in front here. Now that one's doesn't look as closely related to some of these other ones. You might say, hey, we're actually like distributing this n. That relationship's not as close. We do have some other rules as well. So we have log base b 1 is equal to 0. That one I think it's worth taking a look at why that's true. So we have b to the power of 0 is equal to 1. Well, yeah, that's always going to be equal to 1. It doesn't matter what base we put there. That's actually one of our exponent laws. If we look at this one right here. So let's just take an example of, let's say it was log 5. So let's say we have log 5 of 5 equals 1. If we turn that to exponential form, well, that's going to be 5 to the power of 1 equals 5. Well, yeah. So it makes sense that if our base and our argument are the same, it's equal to 1. This one here, I can rearrange and I can actually say, well, if I write this as a logarithm, I have log b is equal to of x, and then this is the exponent I'm looking for. Oh yes, so this has actually just been rearranged. So b to the log of bx is equal to x, and that's just because if we rearrange this, we get this equation. The last one I want to look at, and maybe one of the ones we use the most often, other than these three main ones, is this one here. So log base b of b to the power of x is equal to x. And again, if we actually turn this into an exponent, you see more clearly why this is true. And what it's saying is if I have the base and our argument are actually the same, well, then my exponent that I have here is actually what my answer is going to be for it. Again, I think putting in something else like a number, so let's say 3 so argument 3, power of x is equal to x. And let's turn that into a exponential form. So we have a base of 3x, and then our other part, our argument is 3x. Well, yeah, x is equal to x here. So I don't need to go through all of this work each time.